introduce you tonight Dr. Howie Spiro. Dr. Howie Spiro came all the way up from Davis for us, which is very generous of him, for not very much money. And he's a professor and the current chairman of the Department of Geology at UC Davis. He has more than 100 papers published and teaches courses in paleoclimatology, oceanography, and geochemistry. So he is a world-renowned climate scientist who has recently been on YouTube with a bunch of your research. So please give him a warm welcome, and Dr. Howie Spiro, thank you.
I don't blind you, I can take an airplane out of this thing. This is great. This is a wonderful turnout, so thank you very much for coming out tonight. I've given public lectures before on a variety of things. I'm a jack of all trades. I'm a biologist, an oceanographer. Somewhere along the line, I became a geochemist, and now I'm a geologist in the geology department. And so I kind of do a lot of different things. And lectures like this, quite often, as you can imagine, kind of get into the global warming climate change game. And I had a very interesting experience at a talk I gave a little while ago, and it was an audience, not quite as large as this, but similar, and I was getting ready to give my presentation, and a gentleman walked up, and he says, hello, he introduced himself, and he said, I just want to let you know, I'm not going to believe a thing that you say today, all right, regardless of what you say. And I realized it was very enlightening, okay, because I didn't start out working on climate change in Earth history. I don't really work on the global warming and the climate in the modern, although everything is sort of linked to understanding that. I work on how the Earth operates. An oceanographer, a biologist, a chemist, trying to figure out how the whole system is put together and how the planet works. And sort of that's what I want to do today. I know, as you can imagine, this whole climate, global warming thing is a little bit polarizing today. And so what I'd like to ask everybody to do is to sort of set their opinions about global warming and climate change outside, because we're not going to talk about that. What we want to talk about, all right, is the science of how the Earth operates, the science of how the atmosphere operates, and what we know, okay, rather than what we think we know is going to happen in the future. And I think it's a very important distinction. And then what I'd like to do is hopefully engage everybody to ask questions, all right, that hopefully will allow you to formulate your own opinions on exactly what the heck is going on in this ridiculous climate debate that's happening right now all over the place. So, I'm going to set the talk up so that we talk about how the Earth's climate system operates, how we really why are we warm? Why can we live on this planet? All right. Also talk about carbon dioxide, not from the viewpoint of global warming, but carbon dioxide. We need it. If we didn't have CO2 on this planet, we couldn't live here. We could not live without greenhouse gases. And talk about natural climate variability, how the Earth operates on different time scales, including today. And get into this ocean acidification, which I think we can port over later on in the Q&A part about Lake Tahoe. What is it? Ocean acidification. Personally, I hate this term, and I told my colleagues this. But in many ways, it's an accurate term. It's just that it's a misunderstood term, and I'm going to try to hopefully demystify it. And then I'm going to go back and take you back and how a paleo-oceanographer would go back in time and look at what happened at a very interesting time in the past where the Earth underwent a natural carbon perturbation. A lot of CO2 wound up getting into the system, and what happened to the ocean. I'll show you how we know it was a carbon perturbation. This is how bad it could really get. I'm not going to talk about that. That was another talk. What we're going to do is go into no, I actually deleted this. I deleted this, and I said, how did I get back there? But I wanted to go down to the philosophical challenges. Okay, what are the real problems that we have to deal with as a society rather than, and as well as individuals? I was at the National Science Foundation for 3 years as a program officer on loan from UC Davis, and I got to see a lot of proposals and talk to congressmen and congresswomen. And about the time that I was at NSF up in Washington, D.C., we started to get these papers coming out in cover journals. Everybody was kind of like, oh my God, climate change, everything's going to pot. Okay, so let's just say maybe it isn't, all right? But we'll come back to that question later on. Let's talk about how the Earth operates. The Earth is a heat engine. It is basically an engine whereby the sun heats the tropics. Okay, you can think the sun's out over here, and the Earth is normally tilted. It's not straight up and down. It's actually tilted like this. But the sun is always going to be over some part of the tropics. That's why I call it the tropics, by the way. I asked this on an oral examination once, and the graduate student completely imploded. I said, define the tropics. It was in the title of his dissertation. And he said, it's the place where it's warm. And I said, well, you know, Florida's warm and it's not the tropics. So it turns out the tropics are where, at some point during the year, the sun is directly overhead. The Earth's tilted and is going around in its axis. So it turns out the Earth's tilted 23.5 degrees. So the tropics are from 23.5 degrees south to 23.5 degrees north. This region of the Earth is getting direct sunlight. The poles, meanwhile, are seeing hardly any sunlight. Okay? So basically what you've got is a super hot area and a relatively cool area on the planet, and the whole Earth, ocean, atmosphere system is dedicated to redistributing that heat on the planet. Okay? If we didn't redistribute the heat, you couldn't go to Bremerhaven or Bremen, Germany, which happens to sit at 58 degrees latitude, and be sitting in shorts and a t-shirt, okay, in the summer. It would just be cold. So the atmosphere and the ocean are distributing the heat around the planet. Oh, I'm sorry. You're right. Can everybody hear me? Yeah. Okay. It'll get louder now. All right. So where do greenhouse gases get in? Fit into this whole game. If we didn't have greenhouse gases in our atmosphere, the entire Earth would be frozen, just about, except for places in the tropics. Greenhouse gases are simply gases like carbon dioxide, methane, and other gases that have the ability to absorb infrared radiation in their bombs. Okay? And what's really interesting about greenhouse gases is that they're in incredible trace amounts. You probably have heard, what's with this? Who cares if we go up a few parts per million in carbon dioxide or parts per billion in methane? All of our greenhouse gases are in tiny, tiny, tiny amounts. But there's a sufficient concentration in the atmosphere that the energy from the sun that's basically radiating the planet is absorbed in the bonds of those CO2 molecules and those methane molecules and those nitrous oxide and all the rest of the greenhouse gases. And that heat is trapped in the atmosphere. Now, some of the heat from the sun is reflected back to space from clouds, from dust in the atmosphere, from ice in Antarctica and Greenland. Okay, we know that if you're out on the slopes in North Star, you get a pretty good suntan, okay, in the winter because the sunlight's reflected off the snow. All right, well, that happens also on the planet. We get a huge amount of energy being reflected back to space. And this is kind of a really important point. Over Earth history, the average temperature on the planet is a function of the amount of sunlight coming in, being trapped, and escaping. And when that's in balance, you have some average temperature. If you have more ice on the continents, you reflect more sunlight out to space. The planet gets cooler because now you're not absorbing as much energy. If you have more greenhouse gases in the atmosphere, you have the ability to trap more energy, and the Earth warms up. And we'll take a look in a second about how that operates on geologic timescales. Now, if you take a look at the ocean, what you see is pretty much what you'd expect to see based on this dynamic Earth balance. Let's see, I'm sure mine's going to go off pretty soon. I think I have it on vibrate, but that's all right. Just tell them they can come too. All right, so... they closed the name, so... All right, so
In the tropics, we have the warmest temperatures, and then as you move away from the tropics, we wind up seeing cooler and cooler ocean temperatures. Just what you'd expect based on the heat distribution on the planet. Now for carbon dioxide is not a unique greenhouse gas, but it's an important greenhouse gas. And it's important because it plays a role in a lot of biological and chemical systems on the planet. Now this is the CO2 record coming from the Mauna Loa Observatory in Hawaii, just showing the natural oscillation of carbon dioxide on the planet, okay, over the last 5 years. And it's kind of interesting when you look at this. You can see the heartbeat of the northern hemisphere biota. Okay, you can see the summers in the northern hemisphere forest because this is when photosynthesis starts to put leaves out on the trees and CO2 gets absorbed. And you can see, it turns out, probably May of each year, when the leaves haven't quite come out, but temperatures start to rise and all that leaf litter on the ground gets hit by bacterial activity and respiration, and that CO2 goes back into the atmosphere. So you're looking at this really neat oscillation that goes on in the CO2 record, and this is the mean going through. And one of the things you can see is we're increasing now these values by about 2 parts per million per year. Okay? That's a very clear increase in that we're going to see about 396 May or June this year. We'll hit 400 parts per million about 2014. Okay, remember that 400 number. It's an easy number to remember. Now, all of this comes from a brilliant scientist from the Scripps Institute of Oceanography who in the late 1950s got the National Science Foundation to fund him to put this observatory, which is called the Keeling Observatory, after Ralph Keeling, on Mauna Loa to track the CO2 levels in the atmosphere. And it's dominated, this oscillation is dominated by the northern hemisphere, because the southern hemisphere is mostly water. It's the northern hemisphere that has all the forests. Right? But what you can see is we go from 1959 about 315 parts per million, and today we're almost at 400. Okay? About a 30% increase in the CO2 content of the atmosphere over the last 50 years. What about other greenhouse gases? Okay. Well, we've been measuring greenhouse gases at Mauna Loa as well. One of them in particular, methane. Now remember, CO2 parts per million. Now we're dealing with just parts per billion. Really low concentrations. Methane turns out to be a very potent greenhouse gas because there's so little of it. And it absorbs infrared radiation of a slightly different wavelength than CO2 does. And there wasn't a lot of it. So as you put more in the atmosphere, it sort of absorbs, or has the ability to absorb a lot more infrared radiation. And you can see that basically since 1959, we've gone up almost 70% of methane levels. And we're not dealing with who caused this, all right? This happens to be, has nothing whatsoever to do with human activity. All right? So we get into this, and this is where the problem is. We have greenhouse gases. We know they're increasing. We can measure them. There's no argument about that. Okay? I have been a scientist now working on problems like this for over 30 years. And one of the things that I've tried to do all my life, and all the colleagues that I know, is to get it right. Just to try to figure out what is going on. So nobody's hiding any data. The data you saw is the data that's coming out of Mauna Loa. What comes out to be a problem is when we get into these models. What's going to happen in 2100? What's going to happen over this next 100 years? This is where all the controversy is. All right, so let's not worry about where we're going to be in 2100. Let's just figure out where we are in 2012. Okay, so we talked about greenhouse gases. You can see the greenhouse gas concentrations are increasing. All right, and from what we talked about, if you put more greenhouse gases in the atmosphere, they have the ability to absorb more infrared radiation, more heat. And since we're not increasing the components that might necessarily reflect that heat back to space, for instance, ice turns out to be something that goes in the wrong direction as you potentially heat things up, ice melts. And then you lose that part of what we call the albedo, or the reflectivity of the planet. And one of the things that we can measure from space and with satellites is the amount of sea ice that's up in the Arctic. Now, sea ice is very interesting. It's interesting because it is ephemeral. Okay? This sea ice that's up there hasn't been around for a long time. Okay? It hasn't been around in the sense that ice maybe gets 10 or 15 years old before eventually the bottom of the ice kind of melts away. All right, so what you're looking at in the Arctic is nothing related to sea level. You melt all the ice in the Arctic, sea level is not going to change. Okay, it's something that most people don't think about. This is the equivalent of having a bunch of ice cubes in your margarita. All right, when the ice cubes melt, the level of the margarita doesn't change. Okay, the ice is already displacing the water. The thing you got to worry about is that guy, Greenland. Okay, this is the guy that has that whole bucket of ice cubes that hasn't gone into the ocean yet. All right, into your drink. So you take your bucket of ice cubes, put it in your margarita, and it spills all over the place. Okay, so this is the part that we're concerned about, not the sea ice. But it turns out the sea ice is a much more important component in that this is an area that reflects sunlight to outer space. And as you start to melt it back, the only way you can melt it back from where it used to be is if something got a little warmer. Ice melts. What's kind of interesting about this is that in the past, and I think I can go to the next slide on that. In the past, what we've dealt with, okay, is sea ice up in the Arctic. All right, and I believe that this is looking at 1980, okay, where we had a lot more coverage, but the ice was a lot thicker. Okay, as it gets colder, really thick ice. So what happens for years and years is that ice doesn't melt. It just gets thinner and thinner and thinner until finally the ice is thin enough that seasonally, when the summer starts up, some of it can melt back. All right, and a lot of the ice that we're seeing right now, all right, is 1-year-old ice. It used to be 15-year-old ice, real thick stuff, the stuff that a nuclear submarine would have to punch through to get up. Now, you start to see here polar bears flipping over on the ice floes, okay, because it's not very thick and it can melt over the course of a summer or a winter. Okay, we can see this, we can measure it. And this change is kind of dramatic. Now, when you go to the Antarctic, you see something completely different. When you go to the Antarctic, you don't see any change. Okay, what you see in the Arctic here is this drop in the amount of sea ice in the Arctic, but really, if anything, it kind of looks like the Antarctic sea ice in red is getting greater. Well, the reason for this, and the reason that we seem to have a greater extent, is because of the seasonal dance of the sea ice. So what you're looking at now are the seasons, and you can see how far out the sea ice goes and melts back winter, summer, winter, summer. It's all 1-year ice. It comes, it goes, it comes, and goes. Okay? Up in the Arctic, we have the exact same thing. Okay, except now we're starting to open up vast areas along the perimeter here during the summer. Now you can imagine, if you open up the ocean, and the ocean's not frozen, the temperature has to be greater than 32 degrees, because it's not frozen. Which means that the open ocean has the ability to absorb a little bit of heat from the sun. So each year that we have this opening, the Arctic Ocean gets just a hair warmer, makes it a little bit more difficult for that thick sea ice to develop, and we're starting to melt back the sea ice. Right? This is what we're seeing today. Now, in 1986, something really spectacular happened. Most of you have probably seen the March of the Penguins, the Emperor Penguins. All right? Please do it, okay. This ice sheet right here is the Larsen Ice Shelf. This is that ice shelf that the Emperor Penguins kind of scoot across to get out to the open ocean. And this ice shelf, from the radiocarbon dating that we've been able to do, had been pretty stable back to about 5,000 years ago. And in 1986, and you can see the dates up here, between 1986 and 2002, it shattered and it disappeared. And this is the little peninsula along Antarctica over here. You can see it's just across from South America. We lost this entire ice shelf. This ice shelf was 300 feet thick. Okay, it just shattered, and the way it shattered was lakes began to develop on top of the ice sheet, on top of the sea ice. It's all sea ice, but it's grounded. It's sitting on the bottom. lakes began to develop because of a little bit of melting on the top. Those lakes would then have water flowing down into the crevasses on the ice shelf, and eventually all that water suddenly just shattered the ice shelf. And suddenly you had just all these icebergs rolling out to sea, and it was gone. The problem with this, and we were starting to see it, because all these glaciers that are up on land were buttressed by the sea ice, and now they're beginning to float, and we're seeing it. Okay, so this ice shelf had a lot of surprises. Nobody expected this to be able to go in 5 years. Okay, so that's what we have today. So now let's take a look at the ocean and let's figure out what we can tell from the ocean, and a little bit of chemistry and a little bit of examples now going back into Earth history. And I think one of the most important contributions of the early 20th century to our understanding of how the Earth operates was by this mathematician, Milutin Milankovitch. He was a Serbian, and by hand, no pocket calculators, no iPads back then, in the early 20th century, computed the amount of sunlight that strikes the Earth, okay, as the Earth's rotation, as its tilt, and other what we call orbital type of variations in the Earth's orbit, okay, change with the gravitational attraction of the planets in the solar system. And what he was able to show, for instance, okay, was that something like the tilt of the Earth, which we call obliquity, kind of bounces back and forth every 41,000 years. That's called an orbital change in the Earth. And when the Earth, I'm going to exaggerate, but you can imagine if the tilt of the Earth is tilted over so the tilt is like this, the North Pole is getting a lot more sunlight. And if the tilt of the Earth is less, like this, the North Pole is getting a lot less sunlight. So just by tilting the Earth back and forth with a natural 41,000 year oscillation, we can change the amount of sunlight that strikes the northern hemisphere or the southern hemisphere. This is one of the parameters that on the large natural time scales is controlling the ice ages. Another is something that he referred to as eccentricity. Well, reality, it's just the fact that the Earth goes around the sun in an ellipse. It's not a circle, but that ellipse elongates and gets closer to a circle every 100,000 years. And if you remember way back in your math years, back in high school, okay, I don't remember this specifically, but I've been told this enough that it's true, that the center of an ellipse is not at the center like a circle, it's offset. It's a focus. Which means that at some point, depending on the size of the ellipse, you are closer to or further away from the sun, depending on that ellipse. All right, so if you have your northern hemisphere when you're further away, you're getting less sunlight than when you're having your northern hemisphere when you're closer. Things like this affect the amount of sunlight that strikes the planet. And when you combine all of these orbital parameters, all of these on a geologic time scale, and there's another one in there that they call precession on a 23,000, you wind up with a very complicated signal, okay, that reflects the amount of sunlight that strikes the planet on hundreds of thousands of years timescales. And what we see is that explains the ice ages extremely well. Matter of fact, it explains it so well that the researchers from Europe and the US back in the 60s and in the 70s got funding to go to Antarctica to drill an ice core. And the question they wanted to ask was, do greenhouse gases change with climate? What did it do naturally? Okay, what did it do in the past? So they punched a hole up in the center. Remember, this is that peninsula that we showed where the Larsen ice shelf collapsed. Here's South America up here. In the middle of the ice sheet, where there's some 10,000 feet of ice, at a Russian station called Vostok, European and US and Russian researchers started to drill a hole. And they started to drill a hole down into the ice to collect ice that was very old. And what they were bringing up were ice cores like this. All right, and when they section the ice cores and look at it under the microscope, lo and behold, what they find is gas trapped. And this is the gas from the atmosphere that existed when this ice first formed. And it turns out that this particular ice core had 400,000 years of atmosphere. in it. And they drilled another core now that extends it out to 750,000 years, 750,000 years. And this is what that 600,000 year, now this is age on the x-axis. And on the top is carbon dioxide, and these geochemical, there's methane on the bottom, and this little delta sign with a D is a function of temperature. And what you're looking at is the heartbeat of climate. You're looking at the modern, which we call the Anthropocene or the Holocene, last 8 or 10,000 years. And we go back in time, and you can see this rapid drop into really cold conditions. Okay, this is temperature, so super cold. This is the last glacial period, when there was so much ice up on North America and Europe that sea level was almost 400 feet lower than today. And then as we go back 100,000 years, we hit another warm period. Okay, note the CO2 is high when it's warm, and it's low when it's cold. Okay, we oscillate back and forth, and it turns out that the carbon dioxide concentration in the atmosphere and temperatures covariate virtually 1-for-1. Now that doesn't mean that CO2 is driving the change in climate, or that the climate is changing the CO2. Within the resolution that we can tell in these ice cores, they're changing 1-for-1. When it's warm, we have more greenhouse gases in the atmosphere. When it's cold, we have less. Okay? And I think that you can convince yourself that there's sort of a natural range that the CO2 levels bounce between. Sort of the coldest times when the ice sheets are the greatest, we get down to something about 180 to 200 parts per million. And when we get up during the warmest periods, we get up to something between 280 and 300. Where are we in 2 years? 400, okay? So what you can see in here is that at least in the last 600,000 years, we haven't seen 400 parts per million. What about methane? Well, you go to the methane, same thing. You know, during the ice ages, methane, here's maximum ice age, was about 350 parts per billion. And you sort of get up to about 700. Today we're up to 1,800 parts per billion. Okay, so what this tells us is that as the planet warms, as it cools, greenhouse gases play a role. Okay? They aren't necessarily the trigger, they could be a feedback. Something can warm and then CO2 just sort of helps things along. Okay? But clearly greenhouse gases and planetary temperatures are linked over the last 600,000 to 700,000 years. Now this is just to put that 400 on the scale for the Vostok ice core. Okay, so here we are today. You get that. Here we are today. Here's where we were on the last 400, or actually 600,000 years. We have not seen CO2 levels like this, at least in the last 750,000 years. Okay, so the magnitude of the CO2 today, we haven't seen. Okay, this is the science behind it. This is what we're working with. But the other thing that's kind of very scary is the rate of change. How fast this CO2 is rising. Okay, and we're going to come to this in a couple of minutes, but it's unprecedented as far as the research community can tell for the last 55 million years. And I'll show you what I'm talking about in a couple of minutes. All right, now something interesting is happening with methane. All right, here's that methane rise. Here's by the way, here's the methane today on the ice core record. It's huge. But more importantly, it looks like methane is actually leveling out over the last decade. And what a lot of researchers think is that it turns out methane doesn't hang around very long. Methane is a gas that when it gets into the atmosphere has a lifespan of about 10 years. And then processes in the upper atmosphere break it down, actually break it down such that that methane moves to CO2. Okay, and what we think is happening now is the release of methane, which we think is probably happening from bogs and swamps and termites and things in the tropics, all right, as with deforestation and things like that, the rate of production is now sort of beginning to get balanced out with the rate of destruction. And we're kind of leveling out at this super high level. Okay. That's what we think with the level is coming out. All right, so there's sort of like the CO2 in the ocean and the Earth's planet. All right, now, over the last probably decade, there's been a lot of researchers that have started to look at what they call the other CO2 problem. The Wall Street Journal in January had an article about this. What's the big deal? Okay, there is no doubt that as CO2 increases, a lot of organisms on this planet are going to benefit tremendously. Plants are going to benefit in many cases because plants use CO2 for photosynthesis. But there is a large group of organisms on this planet that will have a negative impact for CO2, and it is driven by the chemistry and what happens when this CO2 sort of does its thing naturally on the planet. So we're going to get a little bit of chemistry, all right, and I'm going to walk you through it, and I'm going to kind of give you some good analogies that you can take home. All right, so we have CO2 in the atmosphere, and now we know CO2 is rising. I mean, we can just measure it, so we know it's rising. Okay, normally CO2 in the atmosphere dissolves across the atmosphere-ocean interface and mixes into the ocean. And when CO2 levels are constant, we sort of have CO2 coming in, CO2 coming out. We call that steady state. As CO2 levels rise, the atmosphere is now seeing more CO2 than it should have. And what's happening is the ocean is becoming a sink. It's basically allowing a lot of the CO2 that goes in the atmosphere to dissolve in the ocean. Fortunately for the ocean, and unfortunately for Lake Tahoe, the ocean has a huge carbon buffer. What that means is that there's a lot of carbon in the ocean, and it has the ability to interact with the CO2 that dissolves in through sort of a relatively easy reaction set from CO2 and water. By the way, anyone know what this makes? See, when you put CO2 in water? Carbonic acid, okay? If you're anyone to doubt that, take your Coke can or take your beer and look on the side and see what it says, okay? The first ingredient usually is carbonic acid. And that's just when you pump CO2 in the water, the CO2 bonds with the water and makes carbonic acid. Now in the ocean, this is sort of a problem, not a bad one, because that carbonic acid right here mixes in with the other forms of carbon that are in the ocean and neutralizes that carbonic acid. Well, it sort of neutralizes it to a degree. Okay, and when I say to a degree, it's because organisms out in the ocean don't necessarily care about the carbonic acid. In fact, they care about the carbonate, the CO3, because that's the stuff that goes into a clam, an oyster, a coral reef, and things like that. They make their shells of calcium carbonate. Okay, that's right. So, take a look at the ocean. What we're seeing, and if you do all the calculations, all right, is that close to 50% of the carbon dioxide that's going into the atmosphere today, based on the calculations of how much fossil fuels we burn and how much coal we burn and everything else, all right, 50% is getting dissolved by the ocean. It's being taken up. Probably a lot worse if it wasn't for the ocean, in the sense that the rise would be much faster. That CO2 goes into the ocean, right, and it starts to react with the carbon system in the ocean, as I just showed you. So here's the CO2, and it reacts, and it starts to react with this carbonate out here, and that CO2 here to make bicarbonate. Unfortunately, organisms don't really care very much about bicarbonate. They care about carbonate. Okay. Now here are the critters in the ocean, corals, pteropods, things like that. Little foraminifera we'll come to in a second. All right, and what they're really dealing with is this stuff over here. So what happens when CO2 dissolves in the ocean? It starts to make the ocean slightly more acidic. It's not making the ocean acidic, it's moving the ocean pH, a measure of acidity, in the acidic direction. But it's not acidic, okay? That's why I hate ocean acidification. It's actually just the movement, the direction it's moving in. Okay, and if you take a look at a pH scale, all right, and you look at the normal range of seawater, well, it's out here. Here's neutral. This is acidic up here. 7 and so on is battery acid. No, worry about that. Tomato juice. For those who eat apples, it's acidic. All right, milk is actually acidic. All right, here's neutrality. All right, so the ocean's around pH 8, 8.1. Okay, stream waters get in the 8 to, actually they get down into slightly acidic values. All right, even precipitation is acidic. And the reason precipitation is acidic because when a rain droplet forms, CO2 dissolves in the rain droplet, makes carbonic acid. Okay, so it's a very weak acid. All right, so what we're interested in the ocean is what's happening in here, and what we'd be interested in Lake Tahoe is what's happening over here. All right, so this is just to show you something and to take home. All right, on the left axis, which may be difficult to see in the back, this is pH, and these numbers are 8.3, 8.2, 8.1, so these are 0.1 pH units. Okay, you can see that here we are in 2000, so if you were to kind of move based on the projections of CO2 and CO2 levels, you'd only change the pH of the water by 0.03 or 0.04 pH units. Negligible as far as pH is concerned. Problem is that there's not a lot of carbonate. And what's happening is the carbonate over here is in terms of 50, 100, 150, 200. There's a very large decrease in the carbonate because there's not a lot in seawater. All right? So what's happening is as you put carbonic acid in, it uses up the carbonate. And there's less available to the organisms to make their shells. Okay, remember pH, it's a log scale. Okay, it's like the Richter scale. You have an earthquake up here. If it's a magnitude 6, everybody goes, oh, I hope I didn't lose the China. If it's a magnitude 7, I hope I didn't lose the chimney. And if it's a magnitude 8, I hope I didn't lose the house. All right? Well, 6, 7, 8, that's 1 unit. The thing is that a magnitude 6 or a magnitude 7 is 10 times bigger than a magnitude 6, and a magnitude 8 is 100 times bigger than a magnitude 6. Same thing with pH, it's a log scale. We always have to keep that in mind as people talk about that. All right, so we have this issue right now where CO2 is going into the ocean. Why do we care? Well, it turns out critters like, tiny little plankton critters that make their shells out of calcium carbonate, look, we lose a couple of coral reefs, it's not going to be too devastating. But you know what the primary food for salmon, young salmon are in the ocean? Turns out to be a little critter called a pteropod that makes a shell out of calcium carbonate. Okay, and that's one of the organisms that's most susceptible to a subtle drop in the pH of the ocean, even though it's not acidic, but that carbonate disappears, they have a tougher time, and it ripples through the food chain. Okay, so what we're going to do in the last 15 minutes or so, 20 minutes, is take a look now, I call it Tales from the Crypt, looking at the geologic record. What do we have to tell about what happened in the past and how confident are we about it? Over the years, the National Science Foundation has funded a program called the Ocean Drilling Program, more recently the International Ocean Drilling Program, IODP. The JOIDES Resolution is the drilling ship that goes around the ocean, and what they're doing is they're dropping core strings, 10,000, 12,000, 15,000 feet down from the surface into the mud at the bottom of the ocean to take a look at the microorganisms, the microfossils that left calcium carbonate shells in the sediment from times past. Okay, so what you're doing is you drill into the deep sea is you're going back in time. You're not a time machine. This is really, truly a time machine. Okay, and for those of you who are kind of interested in history, the very first ship that the NSF used for this was something called the Glomar Challenger, all right, which happened to be the sister ship to the Glomar Explorer, which was the Howard Hughes vessel that covered the Russian nuclear submarine. The Challenger was built to kind of fake out the Russians, and then NSF started using it to drill in the deep sea. There's some really good videos on the web on that. Okay, so we go back in time. What we're looking at are the shells of these critters. These are living planktonic foraminifera. Okay, it's a mouthful of foraminifera. All right, but these guys have been around for a couple 100 million years. They're very good at what they do. They're predators. They live in the surface ocean. These central little shells are made of calcite, calcium carbonate, and these are not big. This is about 0.5 millimeter. All right, so this little shell right here, which when this organism dies, it finishes its life cycle after a couple of weeks, that shell starts to settle down into the deep sea until it hits the mud. And then it just becomes part of the fossil record. The neat thing is that as these guys grow and they lock into their calcium carbonate an archive of chemical information about the environment they lived in when they were alive. And I'm going to give you one more little chemistry lesson. Okay. And it turns out that a very brilliant Nobel laureate from the University of Chicago, who was on the Manhattan Project, this is all from the Manhattan Project, back in the 1940s, came up with an idea that you can use isotopes of oxygen to figure out what ocean temperatures were like in the past in calcium carbonate. And what is an isotope? Well, an isotope is actually an element. We define our elements by the number of protons. So oxygen always has 8 protons. Carbon always has 6 protons. But the weight of that element is a function of the protons and the neutrons in the nucleus. And in some cases, for instance, oxygen has 10 neutrons, can have 8 neutrons. These are isotopes of oxygen. Now in this case, they're stable isotopes. We are all made of oxygen 18 and oxygen 16, different ratios of those two isotopes. They're naturally occurring, they're not radioisotopes, they're not radioactive. Carbon, carbon 12 and carbon 13, those are stable isotopes. Carbon 14 is a radioactive isotope. Turns out that the ratio of this oxygen 18 to this oxygen 16 in the calcium carbonate, CaCO3, is directly related to temperature. And this is an experiment that one of my graduate students, Brian Bemis, ran out on Catalina Island, scuba diving for those live foraminifers. So you go to YouTube and you look me up, you'll find, or a foram's tail. You can see what we do on summers when we're not on Lake Tahoe. All right, and you can see that this is a beautiful relationship. This delta is just a way of talking about oxygen isotopes. That as you change the oxygen isotope composition to calcium carbonate, it's directly related to temperature. Beautiful calibration. This was done on many, many, many animals. This is how confident we are that I can go back 30 million years ago and I can measure the oxygen isotope ratio in my laboratory and figure out the temperature of the water was. And this is exactly how we figure out what climate was like and what the Earth was doing tens of millions of years going back in time. Okay, so let's take a look at one event. It was a scary event once you get a handle on what happened. This is what the JOIDES resolution does. It puts the core string down, drills into the sediment. Okay, from these sediment samples, as you go back in time, we can get lots of microfossils, like foraminifera. And then a laboratory, undergraduates and graduates can pick out different species, and we stick it on a mass spectrometer, which is just a name for a very expensive piece of equipment that NSF hates to give us money for. Okay, and then we take these calcium carbonate shells, and literally we drop it under vacuum and stuff. We drop it into phosphoric acid, and if you take limestone, you drop it into acid, it bubbles. Well, you're making CO2. So we're collecting the CO2 that comes out of this calcium carbonate, which has the stable isotopes of the critters that lived 20 million years ago, and we stick it on the mass spectrometer and we can measure our oxygen isotopes. And when we do that, we get information about ocean temperature and we can get information about the carbon system. Okay? I just described 50 years of the paleoceanography and how we got to where we started to where we are today. All right, now, when you look at this plot, which is a wiggly line, and I'll walk you through it, this is 30 years of paleoceanography publications. And what you're looking at now is an oxygen and a carbon isotope record. All right, carbon on the right, oxygen on the left. All right, that goes from 70 million years ago to the present. So the best way to think of it is dead dinosaurs. Okay, they get knocked out. Right here is 65 million years. Dinosaurs down here, little critters and mammals up here. Okay, and we're not going to talk about carbon just yet. We'll get to it in a second. All right, and for all intents and purposes, the best way to look at this is when you look at these numbers up here, if they move in a negative direction, it's warmer and no ice on the continents. And if it moves in a sort of a more positive direction, so 1, 2, 3, 4, 5, it's colder and more ice on the continents. So you go back to the age of the dinosaurs, and we're sort of in this sort of warmer period of time. And after the dinosaurs get nailed by a meteorite, all right, we come up a few million years, we start to see the Earth getting warmer. And somewhere around 50 million years ago, we are at the apex of warmth on the planet for the last 70 million years. There's no ice on the continents, everything is warm. These are deep ocean temperatures. The deep ocean was 12 degrees Celsius. Anybody has dove in Lake Tahoe, okay, in spring, all right, you know that something around 50 degrees is cool, but diveable, all right? This is not 0 degrees, 32 degrees. This is a warm, deep ocean. The bottom of the ocean is 12 degrees Celsius. All right? And then, from 50 million years ago, climate deteriorates on the planet for a variety of reasons related to mountain building, to weathering, and ice sheets begin to develop over the last 5 or 6, 8 million years over here, and we get to where we are, we have huge ice sheets growing on the planet. All right? So we knew that this existed. This was a compilation that showed us how the climate system operated naturally in Earth history. Now, I was a postdoc at UC Santa Barbara in 1989 when a researcher by the name of Jim Kennett and his postdoc, Will Stott, made a startling discovery. And right about over here, there's this little kind of like bunch of little dots, and the little dots over here, and I can, let's see, does this work? I think it does. Sorry, I'm going to go off screen for a second. Okay, so we will do this. I think this will work. What? Okay, there we go. We're watching plate tectonics. Okay, so we're watching dinosaurs, and then at 64, and this has 65 dinosaurs are dead. All right. So what was going on during this period of time over the last 100 million years is the Atlantic Ocean was opening. India was making a beeline to slam into Asia, okay, to form the Himalayas. Australia has just separated from Antarctica, but in a second it's going to start moving north. And you'll notice there used to be a big seaway up here. But the Mediterranean is going to form, it's the remnant of this big seaway, okay, that existed 20 million years ago, and now it's closing off, and we're getting the Himalayas going off. Australia is now kicking north, okay, and Antarctica is freezing over, and we're pretty much where we are today. So 50 million years ago was sort of like the Atlantic had just started opening, and what Kennett and Stott discovered was this event, this little like pulse right over here, just before the actual maximum temperatures on the planet. There's been a lot of work to kind of estimate atmospheric CO2. We get pretty loose when it gets out back here. All the data that people have collected, it suggested that CO2 levels were a lot higher than they are today. Remember, where this is 2, 4, 6, 8, 10, 400 is where we are today. Okay, and for the most part, 350 to 400 is pretty much what is well accepted for the last 20 million years. And then before that, we started to go up much higher than that. Okay, what about this event, though? This event was very, very scary. Okay, right here. And it was scary for a variety of reasons. The first was, and I was working with the original data set with these guys, we couldn't figure out why it happened. All right, and what happened? Well, you know, it's something where the entire ocean system changed over an unbelievably short period of time. Okay, and this is a core that they took from one of the drilling problems. This is Antarctica down here. And what we see, this is going down, this is dead dinosaurs down here. We're coming up towards the present. And suddenly these isotope chemical compositions of the forame jumped. They jumped across one interval, very, very narrow interval on the core. And the oxygen isotope change, this delta O18, suggested that the deep ocean temperatures warmed up 6 to 7 degrees Celsius almost instantly. Deep ocean, not the surface ship. I sat there scratching, how do you get warm water down into the deep ocean? Because warm water is buoyant, it doesn't sink. The other thing that happened was we had this huge change in the carbon-13, carbon-12, these carbon isotopes, a big spike. Now, this carbon isotope spike is so large, there's not enough carbon in the ocean today to cause anything near this. So something dramatic happened 53 million years ago. And this event, studying this event probably got 20, 30 graduate students and postdocs, faculty positions. And if you include Europe, I would take that to 50 to 60, all right? Because this became the poster child for what happens when you stick CO2 into the ocean and what does the planet do, all right? And it was something that was very, very scary. This change now we estimate to be something across a period of time between about 2,000 and 10,000 years. We can't get much better than that 53 million years ago because of a variety of issues with the cores. So something that took 2 to 10,000 years caused the ocean chemistry to dramatically change. In both the temperature of the deep ocean and the amount of carbon that we have. And to make a long story short, a lot of graduate students and postdocs and faculty were working on this problem, and the only thing that came up that made sense was that there is one carbon sink that nobody had thought about at the time, and it was something called methane hydrate. Now the continental shelves are loaded with methane hydrate. And it turns out methane, under pressure and low temperatures, can get caged by water and becomes that. That is methane hydrate. That is methane. If you were to take a match and light that up after the scientist puts his hand down, it would ignite. Okay? And when methane is in this form, it's locked away. But if you just warm the ocean a little bit, this degrades and all that methane comes loose. And the methane today, at 1,000-meter depth off the coast of California, the continental shelf of California is loaded with methane hydrate. We can see it. We can measure it. It's at 1,000 meters water depth, it's everywhere. And the estimates are something between 2,000 to 3,000 gigatons of carbon, which is now approaching the amount of carbon that people talk about if you burn all the fossil fuels. It's kind of that amount of carbon. Okay? And what they think happens 55 million years ago was there was a methane release because the ocean warmed. The methane came out. Remember, 10 years, methane only hangs around for 10 years. The methane then goes to CO2. That carbon dioxide dissolves into the ocean. Okay? Mixes eventually over the course of hundreds to thousands of years into the deep ocean. And we're along for the ride. So what happened when this went on? Okay, well, this is like kind of the scary part because we can document this. A group of researchers went out off the coast of Namibia, which is the western coast of Africa. And I probably have about maybe 5 or 6 minutes left of the talk, so we're on a good time. And drilled a bunch of cores with the JOIDES resolution, the ocean drilling program, to take a look at what went on in the deep ocean 53 million years ago. What happened to the chemistry of the ocean? The prediction was ocean acidification. Well, that CO2 going in should decrease the amount of calcium carbonate. The organism should take a major hit, and the deep ocean should not be able to accumulate any calcium carbonate. That was the prediction. Okay, and in 2005, colleagues from Santa Cruz and around the world published this paper in the journal Science. And for me, when I saw this about 7, 8 years ago, it was really scary. It was chilling. Okay? Because what they showed was as you look into these deep sea cores, all right, at a variety of different depths, so think of it, one core at the sea floor, 6,000 feet deep, another one 8,000 feet, another 10, another 12. Okay? And what you see in the core, this is dead dinosaurs down here. All right, coming up through time, you see white, that's all calcium carbonate accumulating on the seafloor. And then a very abrupt line here, no calcium carbonate, and it takes some amount of time, which in this case is depth in the core, to start getting calcium carbonate accumulating again. And we put this on a plot, okay? Let's take a look at this. This is the calcium carbonate of the core. Here's the event, all right? We can see that very, very quickly, within this 2,000 year to 10,000 year window, the deep ocean at all the different depths, not a single one was getting calcium carbonate. And we knew there were organisms alive, which meant that the shells that dropped, they were all dissolving on the way down. The deep ocean became acidic, corrosive to calcium carbonate. Everything dissolved. And then, at the shallowest depth, 1,500 meters, within 10,000 years, we start to see the accumulation of calcium carbonate beginning to show up again. At another 1,000 meters deeper, so another 3,000 feet deeper, well, that took 40,000 years before calcium carbonate started to accumulate. And at the deepest core, that's 100,000 years. So basically, this event caused the acidification of the deep ocean. It took 100,000 years for the system to get back to normal, so that the deep ocean was accumulating calcium carbonate. Okay? So this event this perturbation of CO2 into the ocean, something between 2 and 10,000 years to put that CO2 in. Okay? Today, we've basically increased the CO2 content over 50 years, all right, going into the ocean. And how long? All right, now we're getting into some modeling now, all right, but I think this is a pretty accepted number regardless. We have a finite amount of potential oil and gas to burn. And when we burn oil and gas to produce CO2, we just do. It goes in the atmosphere, it goes in the ocean. Forget about the consequences of that. And here we are in 2000, and this is about right. We're putting about 8 gigatons of carbon into the atmosphere today, every year. And now with China coming on board and the third world nations, okay, that rise is going to continue on to about 12. They're estimating about 12 gigatons a year by 2050. And this drop off here is simply because we hit peak oil. The oil's just not there to burn anymore. Of course, there's fracking and there's tar sand, so we have the potential of getting more hydrocarbons. All right, and then within several hundred years we drop off. This event is about 3,000 gigatons of carbon in 200 years. Okay, going out. The other interesting thing about this, and now this is again with the modeling, I don't think anybody's arguing this, is that here we are before we start burning the CO2 rise, and after we get down, we're not putting any CO2 in the system. You'll notice that we stabilize at a much, much, much higher CO2 level. It just takes thousands of years to get the CO2 out of the system. All the CO2 that's going up, you just can't turn the tap off and have it come straight back down again. The ocean has to absorb it, the plants have to absorb it, it has to be scrubbed from the atmosphere. It takes a long time. Time scales that are beyond societal. Okay. All right, so the human issue, all right. This one is one I think that we can look at and ask the question, are humans the culprit in this particular case for this rise in CO2? It turns out there's actually two ways that you can argue this. And both of them, the chemistry is consistent with humans as being the source of the CO2. It's not natural. We've kind of looked at 100,000, 500,000 years of natural oscillation. Okay? And the way you find this out is to take a look at the critters that live in the ocean. In particular, organisms that have a record of the carbon that was in the ocean over the last 100 years. Coral reefs and things like sclerosponges. All right? And what we can do is we can measure, we see the atmospheric CO2 rise, but it turns out that the carbon in the CO2, carbon-13 and carbon-12, plants have a very distinct carbon-13, carbon-12 ratio because they photosynthesize. So if you're making calcium carbonate skeletons, it doesn't really do anything to the carbon, but if you're a plant, you preferentially use the carbon-12 over the carbon-13. And what we can see is, as the CO2 is going up, we're seeing a very large shift in the ratio of these two carbon isotopes of carbon in a direction that reflects plant material being burned. Plant material being broken down from organic matter into carbon dioxide. So the carbon isotopic composition tells us that the CO2 most likely is coming from an organic source. The other one, which turns out to be an argument for why it's not natural, is that in the past, when we've had these natural oscillations in CO2, okay, this is related to just CO2 coming out of the ocean and CO2 going into the ocean. Okay, CO2 basically being broken down, all right, off of plant organic matter, all right, but mostly it's stored in the ocean. One of the things we're seeing with the CO2 going up is you can actually measure the oxygen levels going down. Now, you don't have to worry about it. We're not going to asphyxiate, okay? We're dealing with microscopic changes in the oxygen. And that's consistent for a 1-to-1 ratio in the amount of CO2 being produced versus the amount of oxygen being used, which is what happens when you burn oil and gas, okay? So it does look like we are the culprits for this. All right, so look, I have one more slide after this, And these are the take-home messages that I hope that you got. The consequences, or at least the amount of greenhouse gas that's going into the atmosphere, is incontrovertible. We can measure it. We can see it rise. We can see the methane rise. The levels are very, very unusual for the last million years on the planet. Nobody's hiding data. Okay, no, this is what we're seeing today. Okay, the chemistry and the science is straightforward. If you have more greenhouse gas, just you're absorbing more infrared, the atmosphere is going to warm, and it has to be in balance. Okay, for the planet not to warm up. All right, the CO2 can have a really long-lasting effect. All right, whether it's the chemistry of the ocean or whether it's the CO2 in the atmosphere, we're dealing with timescales that are well beyond a human lifetime and might even be a societal lifetime. And I think that one that's really important is that we're dealing with an issue that's very, very, very scary. It's scary for all of us. Hey, I drive a sport utility, okay? And it's scary because we're being asked to digest a problem on the planet today, okay, whose solution is not going to benefit us at all. We are not going to benefit from this. This is the first true multi-generational problem that we've had to deal with as a society. And, you know, we're not prepared to deal with it. We're just not. And I don't know what the solution is, but the most likely outcome of this is to have an intelligent discussion about what we can do so that 50, 60, 80 years down the line, the system or the amount of carbon we're putting into the system, okay, will be much less than it is today. All right, and that I think is ultimately where the primary issue is. We are on a fossil carbon footprint. We're not getting off of it next year. We're not getting off of it in a decade. We're not getting off of it in 50 years. All we can do to hope is to kind of decrease the amount of fossil fuels and have some other energy sources substitute so that we can reduce the carbon impact on the ocean, the atmosphere, and the ecosystems of the planet. And what that is a discussion that I think from the science point of view, we can probably have to a pretty good degree if we stay with the science. Okay, so that's my take on it, and I hope you enjoy this, so thanks for listening. I am very happy to entertain questions. Yes?
You didn't mention clouds. I mean, if the planet warms, there should be more water vapor, thus more clouds, and wouldn't that cool the planet?
So, very good point, and this is why I stay away from models. There is no doubt that what we're dealing with is not a CO2 problem. We're dealing with a problem that has many, many feedbacks. And it's the feedbacks that most of the people working with models don't have right yet. So, for instance, the question was, if you heat the planet up, you start evaporating more water. If you start evaporating more water, you put more water vapor in the atmosphere, would you have more clouds? And the answer is yes. So, at some point, could clouds actually become sort of that other side of the feedback where they start to reflect more energy out to space? The answer is absolutely yes. Will that offset the heat trapping capability of the greenhouse gases? And I think that ultimately that is sort of where the rubber hits the road. Okay, are those two going to offset each other? Because we are losing a lot of the ice. And we're not reflecting as much. So we have to come up with something else that is going to reflect more in order to mitigate some of that heat trapping aspect of the greenhouse gases. But yeah, clouds, I say to my students quite often, I said, I want you guys to go and I want you to figure out how to do paleo clouds. Figure out what clouds were like during the Ice Age. Because that is one of the big, big unknowns that we have not yet gotten a handle on. Yeah, that's a really good point. Yes?
Is the methane that can potentially be released from the permafrost just a blip in all this?
No, the methane that's coming out of the permafrost right now is substantial and probably is contributing to some of the rise that we see here. Right now, we have a really high methane level in the atmosphere, as you can see from the ice cores. And the fact that we kind of rolled over and we're kind of going stable suggests, given the 10-year life of methane in the atmosphere, that some of that methane that was coming out was part of that dramatic rise in methane. And maybe what's happening now is that methane is maintaining the methane concentrations in the atmosphere by the outgassing from the permafrost. All right, the only way that, in my mind, since these ice cores or the Mauna Loa record is very, very sensitive, if the methane coming out of the permafrost suddenly accelerated, we should see that turn and begin to increase again. So at the moment, what's happening is the loss from the permafrost, maybe the loss along the continental shelf from hydrate from the tropics, we sort of hit now that, I think, that steady state where what you're seeing coming out is sort of now in balance with getting rid of it. Fortunately, if you could, and of course it's all natural, if you could stop methane production, very quickly methane would drop back down again. It would be destroyed. But what's happening with the permafrost is a function of, all the temperature, right? So, yes?
How do you relate the depth of the core where the measurement is taken to the time?
Well, that's a really good question. It's, we have to go 100 meters, 300, 400 feet down below the sediment surface to get back to these ages. And there are a lot of techniques that have been developed over the years to try to get us kind of in the ballpark of where we are. One particular that's used extensively on these deep sea cores, because the sediment pretty much in many cases accumulates at a relatively stable rate, is what we call paleomagnetism. All right, the Earth's magnetic field flips periodically, and we have really good age control on those on those magnetic pole reversals. Okay, so we can go back and say, okay, we're within this magnetic period, which could be 3 million years long. And then once we know, sort of honed in on where we are from the magnetic record, it turns out then there are a lot of extinctions and appearances of different marine organisms in the deep sea. It's called biodams, or horizons at which you can say, okay, these have been calibrated using Milankovitch oscillations, the heartbeat sort of the orbital changes on the planet, to within tens of thousands of years. So we can't get, like today, if I wanted to go into a core and say what happened 15,000 years ago, I can tell you the age of this horizon within 200 years, okay, or better, depending on where you are. When you go back into this period of time, you're probably, a really good age control is several thousands of years. It can't do much better than that, because there's no radiogenic tool or isotope to be able to look and say, this is 53.1 million years ago. So that's how we do it. And it involves a lot of tuning and a lot of data collection in order to get that age model. That is one of the important things about going into these deep sea cores. That's in the back. Yes, somebody. Yeah.
I have a question on albedo, and I was wondering, like you're talking about reflectivity and stuff, and inadvertently that deals with the heating, which you're worried about the CO2 and methane. It's the methane in the bottom of the ocean in the future rising. So I know that human structure isn't necessarily like the cause, but I'm wondering if we were to increase the reflectivity, the albedo of our human, development roads, different things, if that would have, if it's modeled that it would have even like a minute effect.
So I think the question you're asking is, are there ways to increase the Earth's albedo to counteract the effects of greenhouse gases?
Yeah.
So one of the ways that was suggested a little while ago was the natural system would be clouds. Okay, so clouds, turns out volcanic activity, when sulfur dioxide is put up in the atmosphere, it actually reflects energy away from the planet Aerosols in the atmosphere will also reflect sunlight away from the planet. These are all parts of the sort of very complicated ocean atmosphere feedback system that operates naturally. For human activity or human sort of technology to do this, I've heard of some interesting, but I said that kind of a tongue-in-cheek, ideas on how to do this. One was to put out in space a reflective kind of surface so that, some percentage of the Earth's surface is not, sunlight is reflected back to space. It doesn't come down to the Earth. Remember, we're dealing with very, very, very tiny changes in the energy balance. It's not, we're not dealing with large changes. Okay, we're dealing with something where you might have 300 watts of energy per meter squared coming down to the surface, and 150 being reflected and 150 being absorbed, and that's sort of the balance. And now we're at 150.3 and 149.7. It's very small changes. Okay, so one of the possibilities is that you do something that can reflect a little bit of sunlight away from the planet.
And I understand, like, it would just be a small piece of the pie of things that we need to do. I'm just wondering, like, if we were to say, like, roads, human development, like reflectivity, like how cities and things are like urban heat islands and stuff like that, if somehow, like, the reflectivity of that was increased, having lighter surfaces and different things like that, if that would somehow even, like, have a small dent.
It turns out that the problem at the surface of the Earth, you can't do it, and the reason you can't do it is because the carbon dioxide in the atmosphere is not trapping the energy coming down from the sun. It's trapping the infrared radiation from the Earth that's re-radiating back out to space. Okay, so if you do things that will warm things up or reflect them back, the atmosphere still has that trapping capability if you do it at the surface of the Earth. All right, and it makes it very difficult to kind of solve this problem at that end. And also, the magnitude of the problem, given the amount of greenhouse gases that are going in and energy that we're talking about, really the city solution is a very, very, very tiny component. Sort of like having a seesaw where your 200-pound friend is sitting on a really long end and you're sitting up here on a real short one and you're trying to lever the seesaw and you can't get down. Okay, it's really a tiny lever arm, and you really need something that can help to balance the system. Yes.
The example you gave of kind of that fast threshold change was one of a warming, right? The Paleocene. And are there not also fast threshold changes for cooling in the record? And do you think it's surprising that there aren't more of this?
Okay, so obviously, on Tuesday, April 2nd, I started a course called Paleoclimates, and 20 lectures later, we would have gotten to the question you asked. So, in a nutshell, the one thing I left out of this discussion intentionally was the paradigm shifter that popped out of the ice core record called abrupt climate change. And abrupt climate change is a phenomena that we observed that shocked everybody, absolutely shocked the scientific community. And that is that we were very comfortable with these Milankovitch cycles, these really slow, tens of thousands of years changes in glacial conditions and climate related to the orbital configuration of the Earth. And then suddenly, in the ice core records, we started seeing changes in climate of huge magnitudes over 50 years, and cooling events. And one of those, and just to give you a 30-second one-day lecture, okay, it turns out that the ocean, as one of the major transporters of heat to high latitudes away from the tropics, is very, very, very sensitive to changes in ocean circulation. And today, I took this out because I know it's going to run late. And today, we have this vast, what we call the conveyor belt. Water sinks off of Greenland, becomes a deep current, flows all the way around to the Pacific, and a return current. And that water that's sinking in the North Atlantic, okay, is actually the water that's replaced by the Gulf Stream. That's taking heat, hot water from the tropics, from the Caribbean, and moving it up the east coast of the U.S. and up into the North Atlantic. How could you slow that down? If you were to melt the ice on Greenland or add fresh water to the surface ocean in the North Atlantic, the North Atlantic would be less salty. Okay, and if it's less salty, it's more buoyant. And if it's more buoyant, it can't sink. So if you were to, say, add fresh water, which is happening today, and the North Atlantic deep current would slow its sinking, then the Gulf Stream, which is bringing heat up to the North Atlantic, would slow down as well. And what that would then do is mean that you wouldn't have as much heat brought to higher latitudes, the higher latitudes would cool. And so this is the abrupt climate events that we see, very rapid coolings in the North Atlantic. They're linked to things like ice sheet melting and sea ice melting and things like that. Could this happen? Absolutely. The fear of many scientists is not that we feel that this is happening around tomorrow. By the way, you probably recognize this, as the day after tomorrow. That was the whole thing of the day after tomorrow. It actually was based on a scientific theory, and we do see it in the geologic record. The problem is right now is it's not going to cause an ice age, okay, but it could cause cooling, but it's also an uncontrolled sort of cooling. Could the CO2 that we're putting in trigger this? Absolutely, and that could be the big negative feedback. Unfortunately, it's uncontrolled, so what would happen on the other end, we have no idea. The big thing I think that is important to understand is we're dealing with a globally linked system as humans. And all these things you're talking about have catastrophic impact on societies in different parts of the world if they were to happen. And they very well could happen. Okay? But it's very, very scary on the side of the point. But yes, you could cool that way, for sure. Yes.
How bad could it really get?
In what sense? How bad could it really get? Okay, how bad could it really get? All right, I have a lot of colleagues that do the modeling on this, and the 400 part per million level we're going to hit in 2 years is close to where people were hoping we wouldn't get much above in 1992 at Kyoto. Okay, and 450, there's no doubt we're going to see 450 parts per million. We're going up 2 to 3 parts per million a year. I can tell you the year. Okay, just 25 years from now. So you're going to, maybe I'll be around in 25, but 2037, 2038, we'll hit 450 parts per million. If we get above 650 is the number that I heard, which is 2100, continuing business as usual, everybody just keeps burning fossil fuels, the ice sheet can't survive. Okay, that amount of heat trapping in the atmosphere means that the Antarctica, Greenland are susceptible to losing mass. And remember the ice cube story, okay? Antarctica is that big bucket of ice, ice cubes. If you go back to the Paleocene, okay, back 50 million years ago, there were no ice sheets, and you come forward, there's about 220 to 250 feet of sea level in Antarctica and Greenland. I'm not saying that we got to worry about 250 feet of sea level rise. Okay, our lives, don't worry about it. Buy waterfront property. You're not going to lose your home. It's like, there's no problem. All right, but, grandchildren, great-grandchildren, this is the multi-generational problem. And, the discussions we're having today, in the political campaigns and the misinformation that's going on, I'm surprised that we can't at least accept the science that's there, and then talk about what to do about it, rather than saying the science is, the scientists are hiding stuff. I spent my entire career being ethical and just trying to get it right, and I know nobody in the scientific community, and I'm in Europe and everywhere, everybody's trying to get it right. Nobody's trying to hide anything, and so the scientific community is very frustrated because it's all the money, and but we don't We can do what we're doing, and we don't have to worry about the consequences, okay? We just don't. All right, we're talking about 20 ppm, 30 parts per million, you know, maybe hurricanes will get stronger, okay? You know, in California, we don't worry about hurricanes. Earthquakes probably are not going to be affected by any type of CO2 or any type of warming and things like that. But what are we susceptible to? Let's bring it to Lake Tahoe. All right, the regional climate models tell us something. They tell us that less snow. All right, they actually tell us more precipitation, but in the form of rain. Okay, so there'd be less snowpack in the Sierras. And that seems to be a lot of regional climate models converge on this solution that over the next 20 to 40 years, that we will still have snow, but the snowpack will be more like, I'm just using this as an example, maybe more like this year than last year, or years where we call it a normal year. And that has obvious, you know, importance to Lake Tahoe and the level of Lake Tahoe, as well as water resources to the state of California, because we really rely on that really slow release of water into the reservoirs over the course of the year to basically feed Southern California. So, okay, so that's what the regional climate models are converging on. You know, wetter, it'll be wetter, which could be more flooding, but less snow. And, you know, we have a long way to go on that. Drought, well, we've seen it. And you've probably heard that there have been times in the last 1,000 years where we've had 70 years of drought. And I think that if you go, I think that Fallen Leaf Lake has trees that are, you know, dead submerged trees that are 70, 80 feet deep in Fallen Leaf Lake on the south end of the lake. And, you know, so we know that there have been terrible droughts in California over the last 1,000 years. We just can't predict it right now. We just don't know. We don't know what caused it. We're working on it, but we just don't know. In the back, yeah.
Last month, NASA came out with a study where they were, for 10 years, they were watching cloud elevations. And in the past 10 years, they've dropped about 1%. And they think that, they're saying lower clouds help cool the Earth quicker, and they think it's a possible feedback to help fight global warming. And I was just wondering, I guess, if you had heard of it and what you thought of that theory.
I have to be honest, I haven't heard about, it's very interesting. I haven't heard of that study, all right? And, you know, I can't comment on it. I just don't know. So I haven't really heard of it. But thanks for pointing that out. I'll take a look at it. See if I can learn about it and see what they're saying. Yeah.
One of your maps seemed to show higher carbonic acid in the North Atlantic than the Pacific and the Indian Ocean. Is that correct, first of all, and is that related to being near industrialized countries?
That's a really good question. You know what? Have we turned off? We turned that off already. Okay, why don't you turn that back on? Okay, so it turns out that the places where carbon dioxide dissolves into the ocean, as you can imagine, are the places where the water's the coldest, because cold water absorbs gas more than warm water. And the best way to do that, I tell my students when I'm teaching Oceanography 101, is take a can of Coke and put it in the fridge in Davis. I'll preface this in August. And then take a can of Coke and put it out on your back porch, okay, and leave it there for an hour. And then take both cans of Coke out and open the one up that was in the fridge, and you hear a okay, and then open the other one up and you're wearing the Coke, okay? And the reason is because the gas that's dissolved in that Coke at higher temperatures, okay, is much less than in cold waters. Well, it turns out that in the...
Do I guess the right slide?
No, because what I want to do is I want to go to a slide that we haven't, let's see. What I'm going to do... I intentionally took this out. I'm going to go to a slide that gave it another talk. I think this one. But anyway, so that's what I want. Okay, so I'm going to turn up the volume on this so everybody can hear it. Hopefully. All right, so this is the way the ocean operates. Okay. Be nice. Let's put this up.
The global conveyor belt is the major system that carries heat in Earth's ocean. transport of the system helps to moderate Earth's climate. This model shows in a simple way how heat is transported from the low and mid latitudes to the far North Atlantic. Shallow currents are warm and shown as red. Deep cold currents are colored blue. The moving pulse shows the general direction in which ocean currents flow. Cold, deep currents travel east past Africa. Some part of the flow rises in the Indian Ocean. The rest of the cold current continues flowing toward the North Pacific Ocean. In the Pacific, the current becomes warmer and less salty and migrates as a surface current toward the North Atlantic. In the North Atlantic, dry winter air cools the ocean surface. This removes heat from ocean waters and makes them salty and dense. When this water sinks to great depth, the global conveyor belt again begins its worldwide circuit. The entire process takes as long as 1,000 years to complete.
Okay, so this, you just now had, this is like one lecture in my paleoclimates class. All right, so that's the take home. The important thing is that in the North Atlantic, where the water's sinking, it's cold. So it has the ability to pull more CO2 out of the atmosphere, and as it does, that water sinks below the surface. This is one of the big areas on the planet that helps to mitigate the CO2 problem. It takes that CO2 from the atmosphere, moves it away from the surface, and sends it on its 1,000-year trek around in the deep ocean. Okay, another place is down off of Antarctica. All right, so in these cold areas, you have a lot more CO2 going in. In the tropical areas, you don't have as much CO2 going into the ocean because it's warm, and also because we call it the mix layer, the area, the water that can mix, all right, is relatively shallow, and then you hit the thermocline, just like Lake Tahoe, where it's really difficult to get that water at the surface that's in contact with the atmosphere down into the deep ocean. So the big areas where you have CO2 going in are in the North Atlantic and in the South Atlantic, and then some areas over here in the Southern Ocean where water is sinking. Okay, so that's real, and these are the areas that are helping us, so to speak. This Southern Ocean. Remember, this is a Mercator projection. Think of it as a globe. Okay, so Antarctica is down here, so it's a current that goes around Antarctica, and in the North Atlantic. And those are the areas where CO2 is constantly going in, and we already know how deep the CO2 is going because it turns out we have this wonderful experiment that was run in 1952 called the hydrogen bomb. And when the hydrogen bomb started getting set off with air testing, they started producing an isotope called tritium, which is a type of hydrogen radioactive isotope in the atmosphere. And that dissolved in the water. And we have a front, you can actually measure how far along that tritium is in the deep ocean. So we know since 1952 where the water was at the surface and is now sinking. All right, so we can actually see how deep it is, 3,000 meters in the water, and how far south it's gone. Okay? And so we can actually quantify the rate at which the ocean's moving, and then we can do measurements and figure out how much CO2 is being taken up. And this is one of the big areas in and down here in the Southern Ocean.
So 1,000 years.
Yeah, so it takes 1,000 years to go along the conveyor belt. And so here's a little factoid. Okay, everybody knows what carbon-14 dating is. Okay, in some form. Measuring that carbon-14 in somebody in a pharaoh from 4,000 years ago, and you can figure out how old that pharaoh was because the amount of carbon-14 in the atmosphere then, or what the pharaoh was eating, okay, since he died has been decaying. Okay, and how much carbon-14 is left tells you 4,000 years old. Okay, carbon-14 is made in the upper atmosphere, and nuclear bombs. Okay, and so it's the only place it's made. So when CO2 from the atmosphere dissolves into the ocean, sinks, carbon-14 can only do one thing, decay. So you can measure the carbon-14 content all along this path, and you can find that when you get up in the North Pacific, up along the coast of California, that the carbon-14 in dissolved in the ocean has decayed enough that if you were to take a live oyster from Oregon, all right, and eat the oyster, and then take the shell and measure the shell's carbon-14 content and not tell anybody where it came from, somebody would tell you that that oyster is 1,000 years old. Okay, and the reason is because the oyster is making its calcium carbonate shell from the carbon in the water, and that carbon, because it started up over there and made its way around, it's been in the water so long
the carbon-14 content is 1,000 years old. And that's how we know that you can measure how long it takes to get around the ocean. Yes?
This also would imply, just an observation, this imply that based on the prevailing winds that the CO2 produced by North America that heads to the right is going to sink first into the colder waters than that that's being produced by China, for example?
The mixing time of the CO2 in the atmosphere is really quick. It's about a year. So by the time it gets up into the North Atlantic, I mean, we are really, really low mixed. So it's really hard to say CO2 from China, CO2 from the U.S. You know, it's really fast mixing for carbon dioxide.
So if we can take one last question. Guy's been raising his hand for a long time.
Sorry, go. Yes.
Could you have a doctor down here a little trip so he can hear me?
What? You want me to come over here?
Yeah. I came with a friend called Parkinson's.
No problem. Yes.
I'm in 250.
Okay.
And I've been 54 years. And when I live in Bakersfield, and this is little quick, we gave a lot of money to the University of Santa Barbara for geology. Do they still have the geological field camp on Santa Cruz Island? Or can you get us a trip over there?
Okay, the question was, skipping the first part was, UCSB used to have a field camp out on Santa Cruz Island. Is it possible to get an invitation to get on the field trip and get out to Santa Cruz Island? But I'm UC Davis. I used to go to UC Santa Barbara. You have to donate to the wrong campus.
I just like to make a couple comments.
Yeah.
A couple questions that you not necessarily answer, but my impression. Because a lot of things that you have done, I have been involved in the same thing at a different level with research with a major oil company and for about 5 years, I also worked on the geysers, heat, and the geysers, right? Around the heat. My point is, there's no doubt the heat's warming. I mean, there is warming. Probably the CO2 is higher than it ever been. And there are a lot of problems that we don't understand. I think sometimes we shortchange this type of thing. And I didn't hear you mention salinity very much.
Salinity?
What role does salinity play? They vary tremendously in the oceans.
Yeah. So let me start with the first question. So I think that the question eventually got to what is the role of salinity in the ocean. And I think that goes to the question that was asked about rapid climate change, that we have large variations in salinity, and the reason that waters in the North Atlantic sink is because they are both salty and they're cold, and that makes the water mass dense, and it allows it to be able to sink from the surface down into the deep ocean. And the issue on rapid climate change is as you add fresh water from, say, Greenland, to the zone where this water is sinking, the saltiness, the salinity of the ocean gets reduced. The water then is not as dense, it's more buoyant, and it can't sink as rapidly. And because the whole system is very linked, if the deep current can't sink as rapidly, then the warm water current, the Gulf Stream from low latitudes, will slow down, which is because it's replacing that deep water. So the heat transport to the ocean's currents will change, and it's possible to cool the higher latitudes by doing it.
Okay. I just think so much variation in that.
Mm-hmm.
The other thing, methane in the Earth's crust is greater than any other known.
Yeah.
Is that right?
You're absolutely right. And actually carbon in the Earth's crust is greater than that.
Pardon me?
Carbon also in the Earth's crust. But
Methane is really super in the Earth's crust. And my question is, and then that has to do with heat flow, which in my geothermal experience, you didn't just talk about the heat flow here and how it affects climate change. And, you know, you don't have an answer to it, but based on my working with the guys
Mhm.
that the the geysers, that was one of the most important things we did. We had an opportunity also, one time we were drilling a well, we fell, major fall in California. And there are falls in California that have roots to the crust, a lot of falls that don't have roots.
So let me summarize the question, and then I can address it, because they're two really good points. Okay, the first one is about the amount of methane, and I'll also put CO2 carbon in the crust, in the earth. And the second one was about heat flow from geothermal and from the interior of the earth. So let's go with the carbon first, the methane and the carbon. Okay, if you look at the amount of carbon that's in the deep earth, it dwarfs the amount of carbon in the ocean atmosphere system by many, many orders of magnitude. Okay, and I'll just toss out some numbers so you can understand the atmosphere. If you want to, the students can write some of this down if they want. There's a good back of the envelope numbers. The atmosphere has about 700 gigatons of carbon in it. The biosphere, the soil and the forest have about somewhere between 1,000 and 2,000 gigatons of carbon. So the atmosphere and the continental biosphere is about the same. The ocean has about 38,000 gigatons of carbon in it. So the ocean's about 50 times more carbon than the atmosphere, which is why the ocean should be controlling everything, and it has over geologic timescales. When you get into the crust, you've got tens of millions of gigatons of carbon in the crust. So why don't we worry about that? And the reason we don't worry about that for the issues we're talking about now is that the rate of exchange and the rate of movement of the carbon from the crust and the mantle into the atmosphere, okay, is so slow that it doesn't really participate in the climate system per se on timescales of hundreds or thousands or tens of thousands of years. That's the system that operates on the bigger geologic timescales, 500,000 years, million years, to keep the planet's temperature and greenhouse gas content at some sort of equilibrium as plate tectonics take place, things like that. So the carbon, the methane, and the CO2 is not very exchangeable on the rates that we're talking about, and that's why we don't worry about that. Now, from the heat source, the geothermal heat source, that's another good question. If you take a look at volcanism, a lot of people say, what about volcanoes? I'm surprised nobody asked about volcanoes. All right, a lot of CO2 that comes out of volcanoes. And it actually turns out that volcanoes output, and I'm avoiding something like Yellowstone, which was North America killer, okay, that is really taken out of North America. But Mount Pinatubo, which is the biggest eruption that we've had in the last century, okay, the amount of CO2 that came out of these volcanoes, okay, is on the order of about 0.5 to 1% of the carbon, the CO2 that's being produced by fossil fuel burning. It's tiny. All right, it virtually plays no role unless you have a massive eruption. Okay, and we haven't had one of those truly massive eruptions. Okay, now for heat flow, the thing about heat flow is that for the vast areas of the planet, the heat flow is occurring in the deep ocean along the mid-ocean ridges. You've seen these beautiful pictures of hydrothermal systems under the ocean. So you have all this hot water that's coming up and circulating through the regions of the crust that are very close to lava underwater. So there's a lot of heat that's being transported from that contact area with the lava up into the ocean and warming the ocean. But the issue is magnitude. All right, turns out that is a very, very, very small component of the solar warming of the surface, which is far greater than a driver of climate. Okay, so the heat sources that we have in the crust, that we have in the deep ocean, from hydrothermal and from geothermal and things like that, are very local, but not very important on a global scale. And again, if you now go to vast eruptions and releases a lot of that basalt that have taken place at various times in Earth history, it becomes a major role. As a matter of fact, if you go back 250 million years, 251 million years to be exact, okay, Siberia had this massive outpouring
of basalt on the continents. And there was a huge amount of heat and a huge amount of CO2. As a matter of fact, it was so much that it caused the Permian extinction, which took out 90% of the family of organisms that lived on the planet at the time. So there are periods of time in Earth history where geothermal heat flow and CO2 release from these vast volcanic events have had dramatic effects on both the climate and life on the planet. But they're relatively rare, and they really are playing a role over the last couple of million years when we've had the big ice sheets coming and going. So that's really good points.
So I'm going to stop it now because we're way past our normal time.
Okay, thanks very much.
Too interesting
I'm happy to
stuff.
chat.